In this video, we take the concepts of the atomic orbital diagram for the hydrogen atom, which contains just one electron, and extend them to look at the orbital diagrams for all of the other multi-electron atoms. Just to quickly recap, this is the orbital energy diagram for the hydrogen atom that we were introduced to in the previous video. Remember that in this diagram, an orbital, which is just a region of space, is represented by a horizontal straight line, and that orbitals exist in subshells with names such as 1s, 2s, 2p, 3d, 4f, etc. And that these subshells exist within shells, the n equals 1 shell, n equals 2 shell, n equals 3 shell, etc. The characteristics of each orbital can be described using three quantum numbers. N, which describes the overall energy of orbitals and any electrons that reside in them. L, which describes the shape of the electron distribution within orbitals and subshells. And ML, these numbers under the horizontal lines, which go from -L up to +L for each subshell, and which describe the orientation of the electron distribution for each orbital within a subshell. We should also recall that there is one orbital and one subshell in the n equals 1 shell. There are 4 orbitals and 2 subshells in the n equals 2 shell, 9 orbitals distributed across 3 subshells in the n equals 3 shell, and 16 orbitals and 4 subshells in the n equals 4 shell. And finally, the single electron in a hydrogen atom resides in or occupies the orbital with the lowest energy, and we can represent that electron with a single arrow placed on the horizontal line. For multi-electron atoms, as we get more and more electrons in the electron clouds of atoms, the electrons are forced into higher and higher energy levels. It turns out, for reasons we'll go into in the next video, that any single orbital can only accommodate a maximum of 2 electrons. And again, if we consider that an orbital is just a region of space, we can explain this using classical physics by acknowledging that it simply becomes more and more difficult to squash multiple electrons into the same small region of space close to the nucleus, particularly when these electrons all have a negative charge and tend to want to repel each other. So when we get to the third element, lithium, which has 3 electrons in its electron cloud, one of its 3 electrons needs to go into an orbital in the n equals 2 shell. By the time we get to sodium, number 11, with 11 electrons in its electron cloud, we need to start putting electrons into orbitals at these higher energy levels, at the n equals 3 level, and even higher when we get to higher numbered elements in the periodic table. For multi-electron atoms, the shape and orientation of orbitals are the same as those for the hydrogen atom. So orbitals within the s subshells are spherical, orbitals within the p subshells have the dumbbell shape oriented along the x, y, and z axes, and orbitals within the d and f subshells have these exotic shapes and orientations. The major difference for multi-electron atoms lies in the differences of the relative energy levels of subshells within a particular shell. An example of what I mean by this is that the energies of the orbitals in the p subshells are slightly raised compared with their corresponding s subshells, and the energy of orbitals in the d subshells are slightly raised compared with their corresponding p subshells. Likewise, the energy of orbitals in the f subshells are slightly raised compared with their corresponding d subshells. And this is largely due to electron-electron repulsions when more than one electron is present. In multi-electron atoms, the outer electrons experience coulombic repulsion from the inner or core electrons. This means that the coulombic attraction to the positive nucleus is less than would be the case in the absence of the inner electrons. In other words, they are less restrained by attraction to the nucleus than would be the case in the absence of the inner electrons, and the outer electrons are said to be shielded and therefore have a higher energy. We can explain this in a little more detail using the size, shape, and energy of the p orbitals as an example. The 3 orbitals of the 2p subshell are represented in 2 ways here. On the right, diagrammatically, in terms of the shape and orientation of electron distribution, and on the left in terms of their energies relative to other subshells in the orbital diagram for multi-electron atoms. In reality, these 3 subshells overlap the same volume of space around the nucleus and can be better represented spatially by this diagram at the bottom, where we see the 3 overlapping 2p orbitals. If we now consider a multi-electron atom, such as nitrogen, which has 7 electrons in its electron cloud, the reality is that only 2 electrons can exist in the 1s orbital, and we can represent those 2 electrons by placing 2 arrows in the 1s orbital over on the left-hand side in the orbital diagram. A further 2 electrons, and only 2 electrons, can exist in the 2s orbital, and we can represent that by placing 2 arrows representing 2 electrons in the 2s orbital of the orbital diagram on the left. The remaining 3 electrons in a nitrogen atom would be spread across each of the 3 2p orbitals, and we represent that by placing an arrow in each of the 2p orbitals in the orbital diagram, representing a total of 7 electrons spread across orbitals within the 1s, 2s, and 2p subshells. Now, the key to understanding why the orbitals of a 2p subshell are slightly higher in energy than the corresponding orbital in the 2s subshell is because electrons in p orbitals spend, on average, more time further from the nucleus than the corresponding electrons in s orbitals within the same shell. And this is largely due to the size and shape of the p orbitals. This therefore means that the outer electrons in the p orbitals are shielded by the inner electrons closer to the nucleus, meaning they have less Coulombic attraction to the nucleus than would be the case if the inner electrons were not present. This shielding therefore results in electrons in p orbitals existing at a slightly higher energy, slightly further from the nucleus. The result is an orbital diagram of energy levels like the one illustrated here, which differs from the single electron hydrogen case, which had all orbitals within a given shell, or a given n value, at the same energy level. We can see that shielding from inner electrons results in all p orbitals being higher in energy than the corresponding s orbitals within the same shell. The same is true of d orbitals versus p orbitals within the same shell, and f orbitals versus d orbitals within the same shell, where similar shielding effects result in slightly raised energy levels for the different subshells at each n level. An interesting feature of the orbital diagram shown here is that the energy level of the 4s orbital is actually lower than the 3d orbitals. The shielding of electrons in the 3d orbitals happens to such a great extent that the energy of these orbitals is raised higher than the 4s orbital, which belongs to a higher shell level and whose electrons experience less shielding. To complete the picture of orbital diagrams and the electronic structure of atoms, we need to consider 2 new concepts, namely electron spin and the Pauli exclusion principle. And we also need to introduce a 4th quantum number, the electron spin quantum number, ms. And these will be the subject of the next video in this series.